Hello everyone. In this short segment, we'll try to understand two more cases of moving plates or vanes under the concept of impact of jet. So uh, now it's time to understand force exerted on a moving plate held inclined to the direction of the jet. If you remember, in the earlier case, we had a discussion on force exerted on a moving plate where the plate is normal to the axis of the jet, and Fx was rho into a into v minus u whole square, where u is the velocity of the plate and v is the velocity of the jet, which we call it as the absolute velocity. Okay, now let us proceed with the second case. There is a plate which is inclined, and angle theta is the inclination, and this plate is moving with the velocity u, and the jet is moving with an absolute velocity capital V. And if this angle is theta, as we have solved this case in the stationary type, we construct a normal plane, and we first calculate Fn, force, normal force, and we resolve the normal force. Now, if this is theta, somewhere here, if this is theta, we resolve the normal force, and we say Fx is Fn sin theta and Fy is Fn cos theta, because the theta is somewhere here. So let us proceed with the derivation now. So if v is the absolute velocity of the jet, u is the velocity of the plate in the direction of the jet, and if a is the cross-sectional area of the jet, and if theta is angle between the jet and the plate, to be precisely between the axis, the relative velocity with which the jet strikes the plate is not v, it is v minus u. So we are bothered about the relative velocity, and the relative velocity with which the jet strikes the plate is v minus u. And now we'll calculate the mass per second. So the mass of fluid striking the plate per second, mass per second is rho into a into, it's not just v, it is v minus u. It is rho into a into v minus u. Now if we calculate Fn. Fn is the force which is normal to the plate. So it's calculated in an axis which is normal to the plate, and that is Fn. And which is very obvious. You resolve this v minus u in this plane. So it becomes v minus u sine theta, or v minus u cos of 90 minus theta. It becomes v minus u sine theta here, and it is rho into a into v minus u. Initial velocity in the direction of the jet is, this is the direction of the jet now, which is under consideration. This is the direction, normal plane. The velocity before striking is v minus u sine theta, or it is v minus u cos of 90 minus theta. And in the same direction, in the normal direction, there is no velocity after striking. There is no relative velocity or absolute velocity after striking. We have one velocity component here, but that is not in the direction of normal plane. So it is 0. So Fn is rho into a into v minus u whole square sine theta. If you remember, in the stationary case, Fn was equals to rho into a into v square sine theta. Okay. So the component of this force in the direction of the jet, say this is Fx, this is Fx, and this is Fy. Now the angle is somewhere here, that is your theta. So Fx is, and that's why Fx is Fn sine theta, or let's say you consider even this angle 90 minus theta. Fx is Fn cos of 90 minus theta, it becomes Fn sine theta, and Fx is exactly equals to rho into a is missing, rho into a into v minus u whole square sine square theta. Just a correction, we need to have a here, a area here. So it is rho into a into v minus u whole square sine square theta. Now similarly, we can also calculate Fy. Fy is Fn cos theta, or Fn sine of 90 minus theta. So that is rho into a into v minus u whole square sine theta into cos theta. So just by picking Fx equals to something, you can also calculate work done per second, and work done per second is Fx into u, Fx into u, or u is the distance per second. U is the distance per second. See, the velocity is nothing but distance per second. So fx is fx into u, or u is distance per second in the direction of x, and the unit of work done per second is Newton meter per second. And further, you can also calculate efficiency. So the formula is fx into u, rho into a into v minus u whole square sine square theta into u. So let us proceed with the next case. And the next case is the force exerted on a curved plate, or it is a vane, when the plate is or the vane is moving in the direction of the jet. That means the jet is striking at the center. So this is how I can visualize the diagram, visualize the this case circumstance. So there is a v. V is the velocity of the jet, and there is a plate which is moving under a velocity u. So whenever this jet moves with a velocity v and it hits this moving plate, the relative velocity under consideration is v minus u. So the v, or the relative velocity, is v minus u here. And if this angle is theta, you can resolve this v minus u in both x and y directions as v minus u cos theta, v minus u sin theta. Okay. So in the direction of the jet before striking is the relative velocity, that is v minus u, and after striking is minus v minus u cos theta. I hope you know the reason why it is minus. And when it comes to y direction, there is no velocity component of velocity before striking in y direction, but there is one velocity after striking, that is v minus u sin theta. With this background, let us try to solve this derivation. Let us try to have some more equations. So if v is absolute velocity of the jet, a is area of the jet, u is velocity of the plate in the direction of the jet, mass per second is rho into a into velocity with which it strikes the plate, that is relative velocity v minus u. Hence mass per second is rho into a into v minus u. Okay. I hope there is no doubt in coining this as rho into a into v minus u. Okay. Now the next one is force exerted by the jet of water on the curved plate in the direction of the jet. In the direction of the jet always say something related to x axis or in the direction of x. So it is fx. So fx is mass per second into the initial velocity with which the jet strikes the plate before striking, minus the final velocity after which it strikes the plate. To simplify, mass per second is rho into a into it's moving, so it is v minus u, into the initial velocity before striking is v minus u here. It's not v or u, it is v minus u, it is purely horizontal. And after it strikes, the velocity component in x direction is v minus u cos theta with the negative sign. So ultimately, if you simplify, you'll get an equation for fx as rho into a into v minus u whole square into 1 plus cos theta. If you remember, in the stationary case, the formula was rho into a into v into 1 plus cos theta. Similarly, you can also calculate fy. So just to give a hint to calculate fy, so fy is it's almost rho into a into v minus u. There is no initial velocity, 0 minus v minus u sin theta. So you'll get minus rho into a into v minus u whole square into sin theta. So to calculate work done, we always make use of fx in the direction of the jet, not fy. So work done by the jet on the plate per second, work done per second, that is also equals to the power, and work done per second is equals to fx into u. And in this case, especially fx is this rho into a into v minus u whole square into 1 plus cos theta into u. U is the velocity of the plate in the direction of the jet. So summary from this which you can take away is that the cases under moving plate has a direct correlation with that of the stationary cases, and the absolute velocity in every cases of a moving plate or a vane is substituted with the relative velocity. I hope you have understood something from this.